I'm trying to learn from you, and hopefully there would be some correlation here, positive correlation. All right, so I first say very few words about plasmonics and metamaterials, basically 1 or 2 slides. And I also focus on diamond and V centers. I'm a room temperature guy. I believe in devices, and anyway, so it's great to have beautiful physics with low temperature, but when something is possible at room temperature, that's easier. Let's put it this way. And that's actually my take on this. There is this special class of metamaterials called hyperbolic, which seem to be very unusual and could provide some unorthodox way to control the efficiency of quantum optical processes. And that's actually the focus of my presentation. And we are quite proud of recent development in terms of materials, and materials always make a big difference. Like Misha pointed out, I purposely asked this question about whether you could do this single photon, single atom transistor with NV centers and diamond. It's all about materials, how well you could control materials. So we recently really built very unique superlattice, hyperbolic metamaterial, which is of epitaxial quality, and hopefully we would do eventually nice physics with this. All right, so that's the motivation slide for plasmonics and metamaterials. One of the biggest driving forces for plasmonics is basically to help to process information faster, the same as what quantum optics actually is trying to accomplish. At least it's one of the biggest goals, to process information faster. And of course, with existing semiconductor electronics, we are stuck at roughly, let's say, 100 gigahertz or 100 bits per second because of some fundamental delays, such as RC delays. With photonics, I'm speaking now of classical photonics, you're limited only by the Coherence frequency, which is 10 to the 15. So we could hop like 10,000 times faster processing information. But dielectric photonics has a problem of large sizes. With electronics, the size of transistors is few nanometers only. And whereas for photonics, you're diffraction limited, and all the elements which control photons are normally large. And that motivates the field of plasmonics, where we hope to take the advantage of the two worlds, the nanoscale concentration of functionality, if you wish, which you already have with electronics, and the speed which you have in photonics. But to accomplish this, to control photons on nanoscale, you need this metamaterial. So meta, of course, in Greek means beyond. Basically, we'd like to build materials which have properties going beyond of those materials which Mother Nature provides us with. And so the idea here, you build it out of elements which are much smaller than the wavelength, so that you could do this homogenization procedure, introduce effective dielectric permittivity, effective magnetic permeability, but you just design and engineer it, and you obtain properties which you otherwise would not be able to obtain with just existing materials. And to give you examples, I mentioned already a couple, like you could make, for example, metamaterial that have magnetic response at the optical frequencies. All materials in nature, the magnetism dies off when you go to high frequencies. I mean, at optical frequency, all known magnetic materials actually behave in the same way as vacuum, with the accuracy alpha squared, where alpha is the fine constant. So the magnetic response is negligible at high frequencies, at optical frequencies. It's one example. Another example is like negative refractive index, which happens when both epsilon and mu are negative. In this case, it turns out that the phase velocity counterpropagates the flux of energy. So many unusual properties, which indeed, as always, when you have nice physics, result in beautiful, at least potentially important applications. That's what metamaterials are about. And one of the goals which we would like to accomplish with metamaterials to control light on nanoscale. And what we did so far mainly is classical light. And what we would like to do, can we use these metamaterials to control single photons, to eventually being able to control quantum bits. So that's at least the motivation for me, but I guess we need to learn a lot, at least on my side. Well, but what is also important, I was talking about that metamaterials, it's all about design. So you take very small elements which consists of conventional materials, I don't know, like gold or whatever, but you just arrange them in an unusual way so that you get very unusual properties like mu and epsilon, which you wouldn't have with conventional materials. So it's about all this design. And that could result in these beautiful devices such as the hyperlens, which in principle could provide deeply sub-wavelength resolution. Or let's say this type of structure could show negative refractive index, and many others. But what is also important, and I won't speak much about this, but the truth is actually it's one of the biggest efforts in my lab now, it's to further develop materials out of which you build these new structures, because that's really critical. Similar to what happened to silicon electronics, when people realized that silicon is a material of choice, it actually sucked, it was not good at all. And good materials research scientists at Bell Labs improved the properties of silicon dramatically. And now we have all these devices silicon-based. So if you would like something like this eventually happen to nanophotonics, which are based on plasmonics and metamaterials, we really need to improve dramatically materials out of which we build. And unfortunately, materials used so far, gold and silver, simply are not suitable for these applications. Well, to begin with, none of these two materials is CMOS compatible. And of course, if you have already existing industry, $100 billion, so they're not going to change it because we just play with such nice toys. So we better develop materials which do show these plasmonic properties, all this property of localization and many others, but compatible with the existing industry. So I say also a little bit about these new plasmonic components because it kind of integrates with what I'd like to discuss today. So as well, and of course here's our friend Diamond. It's really a cool structure, although we are learning we're far behind what, for example, what Misha already is doing in his lab. But, well, yes, we already discussed it. It's a very stable source, which is indeed very important as opposed to many other light sources, quantum dots, many molecules. This is quite stable source. It operates at room temperature, which is indeed very important. And even at room temperature, you have this very long coherence time in the spin degree of freedom, which is, of course, very important. And eventually, the idea here, of course, is to record these qubits and record and write and read them out with photons, single photons. And for that, you would need this efficient single photon source, and that's actually a specific application I will try to address in my presentation. And of course, well, with nitrogen vacancies, we already have a good source of single photons. But the efficiency is low, meaning that the number of single photons you get per unit time is not as large as you would like to have. Can you kind of speed it up? Can you increase the efficiency of this single photon source? And there are these traditional ways, very efficient, working, beautiful, and I just mentioned just some of them. They are based all on bringing some resonance, basically using the Purcell effect through the taking advantage of resonance. You could use either conventional optical cavity, like the one shown here, or these diamond silver apertures, or this cavity based on a defect in single photonic crystal, or some kind of antennas. It's all resonant type of approach. And the kind of alternative, different approach, which could be considered as a complementary to this one, is based on metamaterials. And that's what I was going to discuss with you. It comes back to the original pioneering work by Evgeny Narimanov and Naida Ingeda, so who kind of emphasized the importance of these hyperbolic metamaterials. Although, as always, they were also earlier work in this regard. So anyway, so what makes them so special? Normally, when we describe electronic or photonic properties, in that sense, it doesn't matter what we do. In K-space, we just find out the isofrequency surface, the surface of constant energy. And for simplest way, when you're dealing with homogeneous isotropic material, the isofrequency surface, which is given by this equation, where epsilon is simply dielectric permittivity, of course, is a sphere. So if your material is anisotropic, so that, let's say, epsilon x is different from epsilon z, instead of sphere, you would have a spheroid. But something really dramatic happens. In a sense, it's like a topological phase transition, if you wish, if one of the epsilon becomes negative. So what it means is that effectively your material behaves like a a conductor, you know that for conductors, epsilon is negative. Like for metals, epsilon is negative. That's why light is expelled from metals. Whereas in another direction, it acts as a dielectric. So that's a very unusual property. If you wish, it's an extremely anisotropic material. What happens in this case? If one of the epsilon is negative, instead of this closed surface, sphere or spheroid, you would get hyperbolic surface, which is open. What it means when I say open, that basically, in principle, theoretically, you have access to unlimited k vectors. Here, the largest wave vector is limited by omega over c, square root epsilon. Whereas here, in principle, any arbitrary k is available. And that's very unusual, and that's why I say it actually acts like, in a sense, like a topological phase transition in k space. And what it implies that if you have access to very large k's, it's like effectively you have arbitrary large refractive index. And this is one of the biggest problems in optics. Refractive index is limited. It's like 1, 2, 3. Okay, so but in principle, that means that effectively you have like unlimited refractive index. But can you build this material? Can you have a material which would behave in such an unusual way that it would be like a conductor in one direction and like an insulator or dielectric in another direction? And the answer is yes. And this is a classical example of metamaterial. So you could take, for example, very thin metallic wires, let's say 5 nanometer in diameter or 10, much smaller than the wavelengths, and make these arrays of wires so that when I average over the wavelengths, since the structure is much smaller than the wavelengths, I could, as always, introduce the effective dielectric permittivity. As you could already guess that in this case, what could happen that effective dielectric permittivity for such a metamaterial consisting of metallic wires and dielectric in between, air or something, could be such that it's negative in z direction and positive in x and y direction. So this structure, unfortunately, is kind of, how should I say, not really planar technology compatible. So it's nice for demonstrations, but if you would like to make devices, you probably would prefer this type of structure. In this case, you build it out of layers, very thin layers, which have negative epsilon. And by the way, when epsilon negative, we call these materials plasmonics, because this is in the heart of all plasmonic applications. Having negative epsilon enables you to have a surface plasmon resonance. And that's exactly what brings up this possibility to concentrate light down to nanoscale. So what makes plasmonic materials so unique is the simple fact that the electric permittivity at the frequency of your interest is negative. So to build this type of hyperbolic metamaterial, one of the ways, and that's what I'm going to talk about, is actually to use these very thin layers of plasmonic materials with negative epsilon, gold, silver, or whatever, and dielectric layers in between. So and again, if the thickness is much smaller than the wavelengths, I could introduce effective dielectric permittivity, and what could happen that in xy direction, effectively epsilon would be negative, so your system would act as a conductor in the transverse direction, but in the vertical direction, it would act as a dielectric. Well, there are many interesting applications for these materials. One of them is a so-called hyperlens, which I already mentioned, which provide this super resolution. You could actually detect and image things much smaller than the wavelengths. But the one I want to focus today on is the very large density of states. And it's very easy to understand. So let's look at two isofrequency surfaces. One at frequency omega, and another it's at frequency omega plus delta omega. The way we calculate the density of states, that's all in k space. We simply need to find out the volume of this layer between these two isofrequency surfaces and take the derivative. And that's actually what the density of states is. And if it's unlimited, as opposed to sphere or spheroid, then the density of states should be unlimited. And that's exactly the property which I would like to employ to control these quantum optical processes. The fact that in hyperbolic metamaterial, material which with this extreme anisotropy, so what happens, the density of states in principle could be anomalously large. And actually, this has nothing to do with resonance. That's what I would like to emphasize. So you can have very large density of states, but in optical cavity, for example, near the resonance, it has singularity, right? And the higher the quality of the resonance, the higher density of states. But that has to do with resonance. Here, as long as my material is hyperbolic, meaning that it's conducting in one direction and dielectric in another direction, the density of states could be extremely large. So it absolutely doesn't involve any resonance, and therefore I call it unorthodox approach. It's a different way to engineer density of states without involving any resonance. And it could be very broadband because in principle my hyperbolic metamaterial could remain as hyperbolic, again meaning that conducting in one and dielectric in another direction, for a very broad spectral range, covering the whole visible, or let's say the significant part of near-infrared part of the spectrum. Again, because it doesn't involve any resonance. It's not of resonant effect. And that's also, well, of course, in reality, perhaps it's a good time now to ask the question, so what the density of states would be limited? There are no such thing as really infinite density of states. And you could guess easily, it's of course the lattice period, the size of these layers or these wires. But the size of these layers could be, let's say, 5 nanometers, which is 100 times smaller than the wavelengths. Normally in conventional materials, so it's all limited by the wavelength. So, and the density of states goes like k cubed, where k is the wave vector. Here instead of k, you have 1 over a, and in principle, you could have truly dramatic increase in density of states. I mean, depending on the design, it could go up to 1 million, okay? Because a 100 times smaller than the wavelength, so you have to take a cube of that. So that's the idea, and so we'd like to apply it for to control the efficiency of quantum sources. So far, let's say the progress which I will show is good. We're in the right direction, but we certainly have not exhausted this approach, and it comes down to the material. We don't have yet as good diamond as we would like. Well, that illustrates my point that according to the Fermi's golden rule, of course, the efficiency of your process, let's say spontaneous emission, because I have in mind this application single-photon source, is proportional to the density of states. And if my source of single photons sitting in the environment of hyperbolic metamaterial, what I should expect, in principle, the density of states where the energy emits to could be dramatically increased, and therefore the efficiency of emission could be dramatically increased. That's the idea. So that's how hyperbolic metamaterials could be used to engineer the density of states and control the efficiency of single photon sources. So this is results of our calculations. So we just took a single dipole sitting at the top of the hyperbolic metamaterial, and this shows the power spectrum, basically the energy associated with these propagating modes. And of course, normally, if k is larger than omega over c, all those components are exponentially decaying. They're evanescent. They cannot propagate. Whereas in hyperbolic metamaterial, all these modes with k larger than omega over c do propagate. So you actually, instead of losing this energy right away, you could propagate it. And these wave vectors associated with these high k modes are much larger than omega over c. And you also get this directionality. Of course, you cannot do it, at least for the hyperbolic metamaterials we are considering, you cannot do it for all cases. So for a particular case, like in this case, you would have this large flux of energy associated with this high k mode going inside of the hyperbolic metamaterial. All right, so from here I'm switching to our very initial experiments. We are just in the very beginning, and good research takes quite a bit of time. I'm pretty much sure in the end we will have very strong results, but what we already have now looks promising, and that's what I'm about to share with you. We started with the simplest hyperbolic material based on classical plasmonic material, gold. And basically, there are only 2 plasmonic materials used so far, gold and silver, but silver is not chemically stable. Therefore, the gold, that's the one which everybody uses. Although I will speak that we have now much better plasmonic materials. So it's like 20 nanometer thick layer of gold and alumina in between. So, and when you look at the effective permittivity of this type of metamaterial, so that's actually was measured by using a spectroscopic ellipsometer. You could see that in the transverse direction, epsilon, you see this is in the transverse direction, it's negative. Whereas in the vertical direction, it's positive. So indeed, it's a hyperbolic material as it should be. So in our first experiment, we just did this very single-minded thing. We placed nanodiamonds on top of this hyperbolic metamaterial. And nanodiamonds we used, in this case, they came from Taiwan. They are like 35 nanometer in size, and they don't have a single nitrogen vacancy center. They like on average 10 centers. Therefore, we couldn't actually have here a single photon source. We didn't measure here G2. So, but at least what we observed in this case that the lifetime actually shrink dramatically from 20 nanometers when you place your nanodiamond on glass to roughly 1.5. Not nanometers, sorry, nanoseconds, to 1.5 nanoseconds. That roughly like 13 times shorter lifetime, which we believe because of these high K modes. Basically, energy from these NV center excitations goes into these high K modes. Okay, but this actually hyperbolic material has a serious problem. That has to do with the fact that when you're working with gold, unless you're doing heroic effort, as recently actually for the first time, and Gennady, who is here, was a part of the team, they demonstrated epitaxial gold, but that really was a breakthrough. It's extremely hard to make. Normally gold, if you make it thinner than, let's say, 10 nanometers, you have this island formation. You cannot really have a continuous layer of gold and have it very thin. So in this case, we use 20 nanometers. That's guaranteed this is really smooth and continuous. But 20 nanometers is comparable to the skin depths, which means basically light doesn't penetrate deeply to the hyperbolic material. It doesn't probe its unique properties properly, if you wish, because you have to make these plasmonic layers thick enough to keep them continuous. It's one thing. And another thing, I told you already that the density of states goes like 1/8 cube. And so the thinner the layer, the higher density of states. So we really would like to make them thinner. So gold actually is certainly not the best material in terms of this, to use it for hyperbolic materials. This is actually a plot which demonstrates this. As a figure of merit for hyperbolic material, we use here the ratio of the real part of wave vector and an imaginary one. Basically, it tells you how well light propagates through your hyperbolic metamaterial. And for the visible, clearly for hyperbolic metamaterials based on gold is not as good as the one on titanium nitride, and that's the one I will talk about now. Even if you go to the near-infrared, then in this case actually you could benefit orders of magnitude. 3 orders of magnitude hyperbolic metamaterials based on this new plasmonic material, titanium nitride specifically actually outperforms the one based on gold. And that brings me to, one of the biggest advantages of this type of titanium nitride based hyperbolic material, you can grow it epitaxially. You can make really very beautiful superlattice out of titanium nitride and dielectric layer. This is your plasmonic layer, this is dielectric layer, and can make it 1, 2 nanometer, 5 nanometer, 10 nanometers, and it would be single crystal quality. That's really the beauty of this. So that brings me to this titanium nitride-based hyperbolic metamaterial. And that effort largely is left by my colleague Alexandra Baltasova. She is actually looking for new plasmonic materials which would be CMOS compatible and in many cases outperform those based on silver and gold. Well, it's a well-known material, and someone coming from Russia, well, actually, that's a true story. When Sasha and I were having a trip to Russia, and we saw lots of churches, and so we heard this story. I tell the story when I give this talk about these new plasmonic materials. So recently there appeared so many new churches, unbelievable, and that has to do with so-called new Russians. I mean, all of a sudden there are many people who became really rich. I mean, like billionaires. Basically taking what used to be the state property and now that is their private property. So anyway, I don't want to go into this, but they probably want to ask for forgiveness. They want to ask God for forgiveness, and they build these churches. But they are still rascals, so they're still smart guys. So it's not gold, actually. They use titanium nitride. That's what I learned when we traveled. So, and if something looks like gold, optically, well, you should expect it should have properties of gold or something very similar to gold. So, and that's
God should definitely know the difference. Yeah, thinking the same.
So,
Very dangerous to try to fool God.
right. Yeah, I fully agree, and in my opinion, they don't deserve God's forgiveness, at least many of them. So anyway, so the problem is how to optimize them. If you buy, let's say, powdered titanium nitride, which you could buy, it doesn't have plasmonic properties. So, but to optimize the concentration of titanium and nitride, it's a non-stoichiometric material. To optimize the structure, that's the work which needs to be done. And it turns out that at least for a number of applications, it would be a separate presentation, titanium nitride indeed does outperform gold, which so far used to be the material of choice. But what I'm talking here about is these hyperbolic metamaterials. But let me just at least mention these beautiful properties of titanium nitride. It's very hard and tough. It's actually used for this high-speed drill. We have at least some people who have hands. I'm not one of them, so I use in their houses. It's CMOS compatible. It's already used as a spacer in transistors and also as one of the gates. So it's CMOS compatible. It's a huge advantage. One of the biggest advantage, it's actually very thermally stable. The melting temperature is 3 times higher than in gold. And the truth is, I mean, as I said, all plasmonic is about concentrating energy down to nanoscale. When you concentrate energy down to nanoscale, you inevitably heat things. And gold actually doesn't sustain high temperatures. Therefore, nearly like any nanoscale device based on gold, the first biggest problem is thermal stability. And titanium nitride nanostructures are by far more stable. That opens up very important applications such as hard disk drives, HAMR, such as thermal photovoltaics. That's exactly actually what we are working now on. But for us, what is also most important, that it's a good, decent plasmonic material, and you could grow it epitaxially. So this actually was quite an effort, because to match the two lattices, you need, remember, for this HMM, you need plasmonic material and dielectric one. And if you would like to have it like a super lattice, you need to match lattices. So the closest to titanium nitride would be aluminum nitride, but it still doesn't match the lattice. And so what we did in collaboration with our material scientists, we added a little bit scandium. These people really can do miracle. And by adding slightly scandium, we accomplished that we exactly match the two lattice periods. So now you could see that this is TM picture. It's really perfect matching of two lattice periods. And this diffractogram shows that indeed you have this epitaxial quality. Well, if you compare titanium nitride with gold and silver, in terms of the real part, it's not as negative as silver and gold, but I should say, again, for some application, particularly for those like hyperbolic metamaterials, the fact that real part is way negative for gold and silver when you go to the infrared, actually it's a drawback. So you could say that silver and gold are too metallic. So why? Because normally you would like to match, when you build in this material with effective dielectric permittivity, it's much easier to design and engineer your metamaterial when you build it out of plasmonic components with epsilon negative, but comparable in magnitude to epsilon of the dielectric component. If one is minus 100, another is plus 2, so you would have to make your plasmonic layer 50 times thinner, which makes it quite often impossible. So it would be nice to have a plasmonic material, for at least for some, not for all, but for some applications, where epsilon is negative and comparable in magnitude to that of dielectric. So in titanium nitride, it's negative, but not that crazily negative as it's in the case of gold or silver. And as for the imaginary part, it's somewhat comparable to gold, somewhat a little bit higher, but the thing is that for gold, what I'm showing here, it's Johnson-Christie. It's basically tabulated data for titanium nitride. It's what we measured. And anyone who worked with gold and built some nanostructure, they know that in reality, epsilon double prime 3 times or 5 times higher. And if you take this into account, that actually they are about the same magnitude. So it's as good as gold at least. And for some applications, actually, like hyperbolic metamaterials, it outperforms simply because its epsilon is not that large in magnitude, which is good, at least in this case. Sure.
What's the plasmonic frequency for this thing? Somehow it looks like it's still...
So it's whenever it's negative, from 500 It's above 500, it's plasmonic.
Yeah, but it kind of somehow looks like it's actually shifted to the left. No?
What do you mean it's shifted to the right? So,
That is actually much more to the left than
right.
It is.
It is, right. But since I have NV center in mind, so for 630, that's what I need, it is plasmonic.
Then the epsilon is actually quite small. It's negative, but it's quite small.
And for hyperbolic metamaterial, this is advantage rather than disadvantage. So if I would have it like minus 100 or 50, it would be a problem for this. For ITAMP, remember I showed this, this one. That actually, why this titanium nitride outperforms gold? Exactly because gold has a larger epsilon magnitude. So, and it is actually a drawback for HMM. So that's what we want to grow. Again, this is just really super lattice. And so that's just to demonstrate that you could make any thickness of this dielectric layer. In this case, it's 2 nanometer. Same true about this titanium nitride. So this is the structure I already showed. This is our hyperbolic metamaterial. Well, and this, again, this is the properties which we measured by using ellipsometry. Well, coming back to Misha's question, so above this roughly 500, it's plasmonic. It's negative. This is and this is plasmonic material, and this is dielectric material. So we are dealing with this is the real part, and this is the imaginary part. So that's the effective dielectric permittivity for my super lattice. So yes, indeed, epsilon is negative above 600 nanometers. So it becomes hyperbolic metamaterial, and this is the imaginary part. Oh, sorry, this is the vertical component, it's positive, and for the transverse component, it's negative. Well, first we check this material by using dyes, because we know everything about dyes. We worked with them quite a bit. So we just place rhodamine 800. You pump it at 635 and look at emission at 715. And so we built many types of these hyperbolic metamaterials, 5 nanometer thick, 10 nanometer thick. So in what we obtain, indeed, there is a decrease in lifetime when you compare the control sample, which is magnesium oxide. And so we also checked how this lifetime depends on the closeness of dye, because we placed a spacer to hyperbolic metamaterial. And these high K modes couple by far, well, better to say this dipole emitter couples much stronger to high K modes if it's very close. So the closer it is, the stronger decrease in lifetime. And actually it goes like 1 over d cubed, where d is the separation between your emitter and the hyperbolic metamaterial. Well, this is calculations, but it's precise calculations, meaning there is no any approximations here. In principle, with this specific hyperbolic metamaterial we have at hand, the local density of states could significantly be larger than in the case of gold-based hyperbolic metamaterial. And you could get this Purcell factor up to 100. And very broadband, as I said. So that's it's a function of the super lattice period. Well, and the rest of this, which I am about to cover, it was done in collaboration with the Russian Quantum Center and the group led by Alexei Akimov. And so they are very smart people, and we are learning from them. So they worked more than we did with Diamond. So this is a collaborative work. This is a standard apparatus to measure this G2 function, which would tell us whether we are dealing with single photon or not. And sure enough, this is a cover slip. And this is on our hyperbolic metamaterial based with layers of 5 nanometer thick. And we do have very well pronounced dip in this G2 function. So it does act as a single photon source. In this case, we use nanodiamonds, which are 1500 nanometer in size. And the problem, I could say it right away, that yes, on average, we do have a single NV center. But it's very hard to control how close this NV center to the surface of hyperbolic metamaterial. And there is very critical dependence in terms of this Purcell factor and in terms of how much you could increase the efficiency of this single photon emission on how close your NV center to the surface of hyperbolic metamaterial. This is one of the things we need somehow to solve. That's one of the problems we are facing. So this is emission count rates. Depending on nanodiamond, of course, this emission depends on the orientation of the dipole moment. Also, as I said, on how far this NV center from hyperbolic metamaterial. But we routinely see, of course, that in hyperbolic metamaterial, more photons actually emitted, the single photons. But we, of course, have this distribution because for different nanodiamonds, you have this NV center located in different position, and the orientation of the dipole moment is different. So this is, again, just one of the nanodiamonds. Lifetime indeed is reduced, as one could expect. And this is statistics in terms of the lifetime for one type of hyperbolic metamaterial, for another one. In all cases, we, of course, see the reduction in the lifetime. So, and if you do this statistical averaging, because we know the size of our nanodiamonds, we could calculate it, and we could measure. And roughly, we have this Purcell factor around 2. It's modest, simply because NV centers are really far from the hyperbolic metamaterial. We need to learn how to place them very close to the surface of hyperbolic metamaterial. And with relatively large nanodiamonds we have now, so the effect is indeed here, but not as large as it could be. And to illustrate this point, I'm showing again this the Purcell factor, which shows that indeed if the spacer, in other words, how close your NV center is sitting to the hyperbolic metamaterial, would be, let's say, 5 nanometers, so then you would have above 100 increase in the efficiency rate of single photons. However, there is yet another problem, and that problem is actually the fact that all this emission goes into propagating high K modes of hyperbolic metamaterial, but that K is larger than omega over C. So to outcouple it to free space, you need to use some structure like antenna or grating, and that's yet another thing we are working on. So let me sum up. With hyperbolic metamaterials, we have kind of unusual complementary, if you wish, approach to engineer and control density of states. It has nothing to do with resonance. It's a very broad band, and it could be interesting to control this efficiency of quantum photonic processes. And we do have first success with these titanium nitride-based hyperbolic metamaterials in terms of observing the increased efficiency rate, but more work remains to be done. Thank you.
Vlad, maybe I missed it, but is there any kind of specific directionality of this photon?
Right. Yes. Normally, this type of structure, there is a directionality. These high K modes actually could normally go inside of hyperbolic metamaterial. However, because we have these nanodiamonds, they also serve as a scatter and decouplers. So some of them does go to the upper half of the space as well. And so far it happens by itself, if you wish. We need really to design a smart structure to collect all those high K modes and convert them into free space, or ideally just to optical fiber. That's what we eventually would like to do.
So this is related to what you were just discussing. What prevents you from sandwiching the emitter between, like, take another strip of these, between two of these? Then the half of the space where it's coupled to free space would actually be taken care of.
Well, at least as it looks now, most of the energy goes inside of material. And but since layers are very thin and not that epsilon is not that large, actually quite a bit of energy does go through material. In principle, I could collect it from the other side. But honestly, we are now thinking about the ways to collect it from the other side. It's all about designing right structure. And we have some ideas, but we don't know which one is the best one. For example, we could actually make a diabatic tapered waveguide of this hyperbolic metamaterial and eventually direct it to optical fiber, because we don't need to send it to free space. We would like to send it to an optical fiber eventually. But how to place close NV centers, I nice we need to work with someone like Misha, because that's still a problem.
So I actually have also a related question. So the problem with all of this lossy kind of metallic material is that you also get this non-radiative damping, just direct, you know. I think it also scales 1 cubed.
Right.
So actually, to what extent can you really kind of make a definitive conclusion about what we see, whether it's radiative versus non-radiative?
No, what actually the calculations, what the calculations show that when you get it closer to closer, then the fraction of these propagating modes starts to dominate. Although in principle you're right, they are lossy. There is of course indeed significant part of non-radiative losses, but there are precise formulas and we use them to calculate. And the conclusion is when you get really close, basically almost 100% goes into these high K modes. That's actually the plot which I showed this previous one. This is exactly high K
These losses are also high K modes, right? So
right, so, but they increase not as fast because in this case you have another parameter, the thickness of layers. So the density of states increases so dramatically that despite the fact that, you're right, non-radiative losses also increase when you get closer. But because of the very large density of states, this channel of transmission into propagating modes beats. And eventually, in this particular case, nearly 99% goes into these high K modes. The question then how to outcouple that. But if you have two channels, radiative and non-radiative, by radiative I mean also the one associated with high K modes, because of the very large density of state, it simply beats. Despite the fact that you're right, that as for dependence on the closeness, it's the same.
Sorry. So actually, I also have a question about this data. So it looks like, certainly in this HMM data, there is a bi-exponential decay.
And it is.
So do you understand why?
Well, because I think because part of that happens is almost like in the free space. It's not sitting right on HMM, and part is associated with first going into high K modes and then being outcoupled to free space.
This is the data for one anyway, right?
Huh?
This is the data for one single.
This is this particular for single one, and the other one is statistics.
So why would? So this 5 nanoseconds is a fast one or is a slow one? Which one is 5 nanoseconds?
Well, this is the long one. The long one. Actually, if you're speaking of this particular one, well, that one we believe is has to do with artifacts, basically measurement thing, the response time of our device. So when I speak of this 5 and 20, it's of course this long one. However, having this said, that these two lifetime we also observed for dyes, for example, and that has to do with the
But
distribution.
it should be different for a single and V center. You should
Right.
not see.
Okay. So for this single one, this is basically artifact. So that's the only one which matters. It has just the way the measurement thing goes.